Come on, everybody. I'm just going to get a few a minute or so to let people join. I can see the participant numbers clicking up now, so I can see people are joining. We'll just give it a minute or so, then I'll do the introductions.
watching.
Okay. First of all, could somebody just drop in the chat box, make sure that you're receiving me okay, that you can hear me, please? Perfect, that's great. I've seen a response. So right, well, good morning, everybody. My name's Paul Walker. I'm part of the Humber region IET network, organising the lunchtime lectures. And so thank you to everybody who's joined us. We've got a lot of people forecast to join us. We're up to just shy of 200 coming up at the moment. So there's lots of people there. That's why you're all automatically on mute. So I'll just go through a bit of housekeeping. So we're looking at around half an hour for this mini lunchtime lecture. We've got two speakers today, Jason Butler and Stephen Holmes. They're going to take us through partial discharge testing. So there's going to be around 20 minutes on the theory and then around 10 minutes on a case study. Regarding any questions, if you want to post questions into the questions and answers box, what I will do is I'll try and keep a track of them because a lot of people might have the same questions, and depending on how many questions we get, I'll pick a couple of the interesting ones out towards the end of the lecture if we've got time, and I'll put them to Stephen and Jason. Any that we don't have time to get through, we will actually package those up, send them through, and we may be able to put responses and then send those out to you later. With regards to CPD, which everybody asks about, after the webinar has finished, we'll be sending a mail out to all registered attendees. On that mail will be the CPD link. There'll also be a bit of information about Stephen and Jason for anybody who's got any interest in what they've said. There'll be contact us there, a website they can go to for their company. And also there will be a survey that we'd like people to complete. Please just tell us a bit about who you are, where you're from. I've dropped that into the chat box already, the link to the survey, but I'll probably post it 2 or 3 times during the call as well, just to keep promoting it. So that's it really. That's all I've got to say. If anybody's got any questions, say pop them in the Q&A box. I'll be monitoring that at the same time as the webinar is going on. I'll be going off video as not to distract you all, so you can concentrate fully on the lecture. So I'll hand over to Stephen and Jason and let them introduce yourselves and get on with the lecture. So I hope you all enjoy it. Thank you very much.
Thanks, Paul. Thanks for the introduction. Stephen, Jason, looking forward to filling your lunchtime with some education and a small case study. We've got half an hour, so we're going to crack on. And so, Steve, if you can share the screen, please, and then we can start presenting and hopefully give you something interesting over your lunchtime. Okay, so partial discharge awareness. Now, for those of you who know Pumptec, we've been maintaining pumps for commercial and industrial clients for over 20 years, but recently we've actually moved into doing PD surveys for some of our clients who've requested it. The presentation we're going to give will cover quite a lot of the technical detail behind partial discharge, but we're going to use one of the surveys that we've completed with one of our clients to answer the key question, which is, okay, what do I do now you've found PD? So we're going to start about what is partial discharge, why is it important, how we detect it, and then after about 20 minutes, we'll move into the case study. Really importantly, it doesn't prove yourself competent for going into a high voltage substation or for detecting PD. They are very dangerous environments. Steve.
Okay, thank you, Jason. So let's look first of all why we want to condition assess any electrical asset. And there's three major reasons. First of all is safety, your safety in visiting the area, safety of your staff, safety of the plant if there are explosive atmospheres or whatever in the area. And then nobody wants the lights to go out. Nobody wants production to be lost. Nobody wants interruptions to power. And so that's why we'll be condition assessing. And thirdly, is asset management. Now, if you're managing high voltage assets or any assets, understanding the condition of them is a major part of your planning operations when you start to look at either replacing the assets or refurbishing them. So, and condition assessment is an important part of that process. So that's conditioning assessing. So why partial discharge in particular? Well, partial discharge is related to insulation failure, and it's estimated that 85% of disruptive HV switchgear failures, for example, and that is when the lights go out, I mean disruptive, are caused by insulation failure as opposed to other causes. And partial discharge is an excellent early indicator of insulation breakdown. So what is partial discharge? Well, if I can paraphrase the IC definition, it's a discharge that does not completely bridge the electrodes. So in the picture here, you can see there's an electrode separated by insulation, another electrode. And then in this particular instance, where we're thinking of a solid insulator, and there's a small void between the two, and across that void is a small arc. Not an arc that bridges the electrode, but just across the void itself, where the insulation is not present. Now, you can get partial discharges in fluids. They're a bit more difficult to picture, so that's why I've used a solid here. We also encounter different types of partial discharge. Now, these definitions are largely accepted in the UK and Europe. Our American colleagues have a slightly different view of the world. There's like subgroups of partial discharge. But if you use these in the UK and Europe, you'll be more than understood. Corona discharge is the type of discharge which occurs in the air or gas around a conductor. And it's very common on outdoor equipment, overhead lines, outdoor switchgear, particularly around sharp points that have either deliberately or accidentally been left on a conductor. And it's relatively harmless. It does produce a little bit of corrosive gas, but that's washed away by the rain and blown away by the wind. Surface discharge is more concerning. This is when we get discharges down the surface of an insulator. It's sometimes known as tracking, and this can ultimately lead to the breakdown of that insulator, particularly on resin and plastic insulators that we see so commonly in indoor equipment these days. And finally, internal discharge. Well, this goes back to the picture we saw earlier. This is the breakdown within voids within an insulator, and this can grow. And when it does go to a full arc, a full discharge, there's nowhere for the heat energy to go. So this one is very destructive and can cause fires and explosions. Luckily, of the three, it's the less common. Let's look first of all at the progression and damage of internal discharge. Back to our picture and the little discharge. And this can erode away the void, similar to arc erosion. Eventually it will carbonize the surface, that little void, and the partial discharge will extinguish. So good, you may think, But what effectively happens is you increase the voltage stress on the rest of the insulator. So if there are any other imperfections in the insulator, these will then start partial discharging. And of course, these in turn then carbonize, and eventually you end up with catastrophic failure. Here's a picture. This is an open source picture from Wikimedia of a current transformer that's been sectioned in two. You can see that there is a conductor down the middle of the current transformer, the primary of the current transformer. That should sit in a nice, neat passage between the resin, a straight line. Instead, you get a wobbly line where it's beginning to erode the insulation. And eventually it will drive a little mouse hole between the primary and the secondary, and that will cause a fire or explosion. You can also see the corrosion damage as well around there. Surface discharge progresses in a slightly different way. Here we have a single point discharge that is growing down an insulator, and it's leaving behind a carbonized trail. This splits and divides a bit like a tree growing down, sometimes known as treeing or tracking going down, and may split into several different routes going down. Eventually it produces a carbon track that goes all the way from the conductor to Earth, and hence catastrophic failure. There's a bit of chemistry involved as well. This happens with surface discharges and indeed corona discharges if they're boxed in. When the discharge is in the air, then the oxygen in the air produces ozone, O3. This ozone readily reacts with nitrogen and water in the air to produce nitric acid. And that nitric acid goes on to corrode any iron-based materials, steel, etc., to produce rust, and will produce verdigris on any copper-based materials. The ozone, interestingly, also reacts with aluminium trihydrate. Now, this is a fire suppressor that's very common in plastic and resin insulators. And it reacts with both sides of the chemical equation. It reacts with the aluminium to produce aluminium oxide, white powder, which is a very good telltale sign that we've got trouble in the area. And it also produces water. And that water actually makes the discharge worse. So we've got a bit of a chemical chain reaction going on here as well. A lot more pictures of surface discharge, again from Wikimedia. We can see pictures of partial discharge, tracking across surface of insulators. And this is from used by permission from Jones and Father company of a discharge activity on a termination. And similarly with this one as well, you can see the white powder on both these two instances and the area charring on this one of the discharge. Now I'm going to introduce phase plots because this is important for our case study later. And this is where we plot the activity, the partial discharge activity over the main cycle. So first of all, if we were to look at internal discharge, what we'd get is one little current spike every time the discharge, the mains voltage becomes sufficiently high. So you get one on the rising waveform and one on the falling waveform. Typically 1 to 2 pulses per cycle, but perhaps more importantly, the pulses tend to be 180 degrees apart or thereabouts. They do jitter around quite a bit, so over several cycles, they won't always fire at 75 degrees. You know, some will fire at 77 and then they'll fire at 70 degrees, etc. But the important thing is the groups of pulses will be 180 degrees apart. If we look at surface discharge, what we tend to get are smaller pulses, but more of them. And these, again, will appear on the rising waveform and on the falling waveform. In 10 to 150 pulses per cycle, thereabouts. And again, importantly, the groups of pulses are 180 degrees apart. So that's partial discharge. Let's have a look at ways that we could possibly detect it. And we want methods which are non-intrusive. So we're not going to be doing any complex measurements. We're not going to be making any dangerous connections or removing covers or anything like that. We want a system where we can take a measurement and move on quickly. And there are various physical characteristics that a partial discharge gives off, which we could use potentially for measurement. It gives off a little bit of light, but this is very difficult to see unless you're in the right lighting conditions, usually only visible in the laboratory or by using a UV camera, an ultraviolet camera. And these are quite popular in America for looking at overhead lines. They're rather expensive, and you have to point the camera directly at the source of the partial discharge. So not much good for typical indoor switchgear. They give off a little bit of heat, but that heat is very localized. It's very intense, but localized. And yes, if you can point your infrared camera directly at the source of the partial discharge, you will see it. But again, it's not much help for a typical indoor medium voltage switchgear because there isn't enough energy to heat up a complete panel. So you won't see one panel that's warmer than another one just because there's a partial discharge in behind it. Smell, the characteristic smell that old timers in the industry will recognize is a smell of ozone. They describe it as somewhat similar to the smell when you're arc welding. But that smell is actually nitric acid that you're smelling, and it's a very unreliable way of detecting whether there's partial discharge there. So I think we can dismiss that for now. So what we're going to focus on is electrical and electromagnetic techniques and sound, and in particular, ultrasound. There are various different techniques for detecting partial discharge using electrical or electromagnetic techniques. Now, we haven't got time today to go into all of them. So here's a list, and then I'm going to focus in on the last one, which is transient earth voltage. Why this one? Because it's a good all-round technique for indoor switchgear, for example. It's very easy to use, it's very flexible, and is of great use. And to explain transient earth voltage, I'm going to introduce you to my all-purpose high voltage asset. This is very simple. The diagram, you've got a high voltage conductor surrounded by insulation, and in turn surrounded by an earth metal enclosure. Now I'm going to introduce a partial discharge into that insulation. If we were to measure the current waveform using an oscilloscope on that conductor, every time that partial discharge flashed over, then we would get a small current kick on the oscilloscope. And indeed, that's the basis of one of the techniques that I mentioned earlier, the IC, or apparent charge technique. Not very practical to use in the field because it involves making connections and elaborate equipment. So luckily, when there's a current kick in the conductor, there's a similar equal and opposite kick on the surrounding metalwork. Remember, all this is high frequencies now because the pulses are very high rise times. And so they're full of high frequencies. And also because they are full of high frequencies, that current has a distinct impedance between the point of measurement and true earth. It might only be an ohm or two, but it's enough to create a voltage spike, which we can measure more easily. How do we measure that voltage spike then, which we know as a transient earth voltage, TEV? Well, what we do is form a capacitor. And one plate of the capacitor is inside the instrument, and the other is the earth metalwork of the HV enclosure. And the dielectric is the plastic of the instrument's enclosure, and the paint or the coating of the HV asset itself. So we've formed a little capacitor here, and when the high frequency pulse goes whizzing by looking for true earth, it gives a kick to the millivolt meter, and that's what we record as a transient earth voltage. Now, the beauty of this technique that it's very easy to do a measurement. Here we see a guy also from Wikimedia doing a a TV measurement on some switchgear. He's got his instrument placed flat against the metalwork, and he's forming that capacitor and allowing the instrument to record the voltage pulses that are flying across the metalwork. No connections made, no covers removed. This is an excellent technique for detecting internal partial discharges. If, however, we want to look at surface discharges, we need to look at another technique, ultrasonic detection. Now, in the severe cases of ultrasonics, of PD, surface PD, we might be able to hear that ourselves. But by that time, it's a little bit too late. So it's best to detect the discharge early using an ultrasonic instrument. The typical sort of energy, maximum energy, is around about 40 kilohertz, which is about twice the frequency a baby can hear and about 4 times the frequency I can hear with my ears. So what we want to do is move it from 40 kilohertz down to 5 kilohertz and represent it in a pair of earphones or headphones, and there we can all comfortably hear it. And it's important to understand that this is a qualitative measurement rather than quantitative. What we're listening for is the correct noise. So I'll give you an example of this. So the correct noise is like a fizzing or popping or a buzzing noise. Sounds a bit like what you might hear if you stood under a transmission tower on a damp day. It can often fade in and out with a low repetition frequency as well. And it's important that it has that sort of crackle to it. Once heard, never forgotten, basically. Detecting with ultrasonics, you can use an ultrasonic microphone. Now here we have another view, a HV asset with the conductor in the center and the discharge on the far side, but that's no problem because the sound will bounce around the chamber and appear out any screw hole or slot or grill that happens to be in the switchgear. Now this is very easy to do on older switchgear. There are plenty of gaps in the metalwork for the sound to escape, but on more modern switchgear, things tend to be a bit more sealed up. Those natural holes don't exist. So here we can make use of a magnetic contact probe. And this places a ultrasonic microphone up against the metalwork, very sensitive microphone, that's listening for the vibrations coming through the metalwork, and that then is passed on to the instrument and into the earpieces of the operative.
Steve, thank you very much. That covers really in the 20 minutes of your half-hour lunch break, a little bit about the theory of partial discharge and why it's important and how we go about it. Usually though, at this point, we try to go large and dramatic with, wow, partial discharge, destruction and chaos everywhere. So not to leave you disappointed, we've got a little bit here of a large and dramatic partial discharge source. Clearly that's large and very dramatic. But what we're actually going to be doing is looking at a UK automotive manufacturer, proactive, good client of ours, and was concerned about early signs of PD. So what we did, we went over and we did a partial discharge survey, and we found a couple of transformer terminations that had small issues with them. And that gave us the questions which the case study is going to answer. You know, enough time to monitor, enough time to plan actions. And really, what came across very strongly was the fear of production loss. Not the unplanned, but also, do I need to do a shutdown? Do I need to take action? So, Steve, if you can carry on with the partial discharge, please.
So what we're going to look at is 2 transformer terminations, and back to our friend, the phase plot. And these are phase plots that are taken with portable instruments. But unlike the ones we saw earlier, you can't see the mains waveform, but we do have an x-axis which runs from 0 to 360 degrees. The absolute position of the partial discharge is not important. What we're after is that separation by 180 degrees. And you can see two groups of activity here. Each little dot is an event, and there are two groups of events, one just before 180 degrees and one just before 360 degrees. Now, this is very low magnitude stuff. It's sort of averaging out about 16 dBs. And the pulse count is between 1 and 2, so we think it's a very small internal discharge. Something worth keeping an eye on, but nothing to be too concerned about for the very short term, at least. And here's another one. And again, the eagle eye amongst you will spot the two mounds of activity. This one just before 90 degrees and another one just before 270 degrees. The interesting thing about this one is that there was quite a bit of noise which on the circuit, perhaps produced by localized electronics in the vicinity, which was actually masking the partial discharge from the operative, me in this case. And I didn't see it until I got back and analyzed the data afterwards and said, there's another one. And again, it's very small magnitude, but we've caught it early, which is always good news. So does it answer the so what question? So much for all the clever analysis, etc. The so what questions are key for industrial sites, certainly. Do I need to take action now? What actions will need to be taken? And the one that I get asked over and over again is, can it wait until the next planned shutdown? So let's have a look at those questions. Do I need to take action now? Yes, but the only action you really need to do is to increase the frequency of a PD survey in order to establish the rate of deterioration, and possibly to restrict access and enhance the PPE requirements, particularly during switching. Ultimately, what actions have to be taken? We need to confirm the location and then possibly re-terminate those terminations. Can it wait till the next planned shutdown? In this case, with additional monitoring, yes. The internal discharges are unlikely to grow fast at 11 kV, so time in this instance is on our side, and it could wait for the next annual shutdown.
Well, you've had 30 minutes. Hopefully you've had cake and coffee in your packed lunch, and hopefully you've found this useful. We would love to be able to answer some questions for you. My contact details are there. If you've got some queries, let us know. Equally, if you or your teams want a little bit more detail, give us a shout. We can run one of these for yourselves as well. Apart from that, I'm going to hand back to Paul and say thank you very much for your time, and hopefully you found it useful.
Okay, thank you very much. That was excellent. Well, I hope you all enjoyed the lecture. I found it interesting. I'm not an electrical expert myself. It's not my discipline, but I managed to follow it. So it's pretty good. Thanks. I've got a few technical questions for you, if that's okay. If you don't mind answering a couple, I'll try and pick out some ones that are interesting. So one from Tim. Can you see partial discharge using a power quality meter connected across the LV control circuit?
No. LV control circuit, I'm not quite sure what you mean by that, but first of all, this is a high voltage phenomenon. We don't see it at low voltage. If you wanted to put something like a high quality a power quality meter on, you'll be doing roughly equivalent of that IEC measurement by putting an oscilloscope effectively on the conductor, the high voltage conductor. And that is done, but as I say, it's not very practical for field use.
Okay, thank you. Chris from John says, he finds that fluorescent lighting corrupts his readings on his TEV. Is this something that you've experienced?
Yes, yeah. In fact, on the case study, you had to do one in the dark, didn't you?
Yes, we had to switch the lights off. So yes, it's always useful to make sure you've got your head torch with you when doing the PD survey, because that can occur. I've never worked out why some fluorescents interfere with TV and others don't. There's so many different types, but yes, there are occasions when you have to put the lights out and use your head torch to record the readings.
I mean, it's certainly one thing to consider before you quickly have a shutdown. You know, make sure you've identified where it's coming from, whether that be somebody welding outside, or it could even be a flicker from the lights. Confirm it a couple of times if you're going to shut down an oil rig or a process beforehand. You know, make sure you get a second engineer to look at your results.
2 or 3 people have asked if it can be used on HV cables, or those equipment.
The techniques that we described today can't be used on HV cables other than terminations. Mind you, a lot of the problems that you get are actually in terminations. And indeed, if you can get access to joints, assuming they're not buried, you can use TV techniques as well on the joints themselves. But the technique for using it on cables is another one that was mentioned in my list of electromagnetic techniques, which was the RFCT. And that's perfectly possible if you can get access to earth straps. Now, some people have earth straps on their cables, and other people don't even know what you're talking about when you mention an earth strap. So it really does depend on localized installations, on whether you can do an online PD measurement on a cable or not.
Yeah, we're quite happy if you want to take our details to go through cables as well.
It's another 30-minute presentation basically to do PD on cables.
Yeah.
As another theme here, a couple of people asked around, can you monitor it to it? Is there a point where a little bit of PD is okay, and then it passes like a trigger point and you have to do something about it, or you can monitor patterns? A few people asking how.
I think this is down to your own risk appetite, to be perfectly honest. You know, part of this is consider having a slow puncture. You know, at what point do you address that slow puncture? You've all got, on modern cars, you've got your tyre pressure being monitored. If it's going down very slowly and you're just pootling around to the local shops, you make a judgment. If it's going down quickly, the rate of change is accelerating, and perhaps you're going to visit somebody a bit further away along the motorway, your risk profile says, no, I need to get something done about it. There isn't, I'm not sure I've ever heard of good PD. Have you ever heard of a good PD? But there's manageable PD.
Yeah, manageable PD.
And it's understanding the rate of change of the deterioration, and equally, like all risk, the consequence of risk, what's attached to that circuit and what would happen. So again, it's a bit of a judgment call, to be honest.
Okay, thank you. I'm going to do one more. Apologies if you've asked a question and it hasn't been answered. We've got 269 people have dialed in, and there's a lot of questions, so I'm trying to pick out what I believe to be some of the more interesting ones. A nice easy one, I think. What's the lowest you can go down to when we're saying HV? 3.3, 6.6? What's the lowest
voltage? Well, practically 3.3. It almost becomes irrelevant at 3.3 kV to do partial discharge. The partial discharges, will they even exist at 3.3? Theoretically, they can exist at 1,000 volts and slightly below, but in practical cases, it's very rare to see it at 3.3. And we're now, most people would say that is the limit, the lower limit. Certainly by the time you get to 6.6, then you're away.
That's great. Thank you. I have captured all the questions from the chat in a. I've downloaded it from the chat box, so we can take the questions offline and have a look. Okay, so a lot of people asking around CPD, is the slide deck available, is the video available, all those type of questions. So I can summarize that in one response, which is that will be all registered delegates will be contacting after the event in the next day or two with an email, and that email will contain a link to the CPD certificate that you can download yourself from the link that I'll send. And if the slides and if the video is available, they are not always available, but if they are in this case, it'll be confirmed and we'll include it in that contact we make with you. So hopefully that answers those questions for everybody. So we've gone a little bit over a half an hour, but I think it was certainly worth it because some good questions and some excellent answers. I'd just like to thank Jason and Stephen one more time for taking the time out of their schedule to present to us. And I will also be posting one last time the link to the feedback questionnaire in the chat box. If people take the time to fill in the feedback questionnaire, that'd be fantastic. So hope you all enjoyed it, and I'll let you get back to the rest of your days. Thank you very much. Goodbye.
Thank you.
Thanks very much. Bye-bye.